Okay, well, let's go ahead and get going. I'd like to welcome Alan Stern to our environs there, and really looking forward to his talk. Alan is the founder of the Solar System Science and Exploration Division, the office up in Boulder. You know, that was his idea, and he got it started and create a really fantastic group of researchers up there. That's been very vibrant. He's also, of course, the PI of the New Horizons mission, which we'll hope to continue for a long time with the current team and Planetary mission. And also, I'd like to point out a fun fact that Alan is the person who invented the term dwarf planet back in the early 90s when he was speculating that there could be thousands of Pluto-type objects out there, and so he came up with that moniker for that class of planet. So Alan, I will turn it over to you.
Well, thanks, Mark. Thanks for inviting me. Thanks, everybody who's in the room for coming and listening, and the same to everybody who's online. It's great to be back in Tucson, even if briefly. I'm down here in between.
Alan, you got muted. Could somebody unmute Alan?
Alan, you should be able to do that from the top of the seminar thing. Just hit the unmute.
Oh, okay.
Is that working?
That better?
Can you hear?
Oh,
It's all good?
All good.
Okay, great. Yeah, so I was just saying thanks. I'm down here in between being up at Flagstaff for the Lowell advisory board meeting, and then go back next week for ACM. This is supposed to be a fun talk. It's kind of like a lunch talk, except there's no lunch. But I only have 30 slides, and there's lots of time for discussion, questions, spitballs, all that. It's a hobby project of mine, something I'm interested in the field of astrobiology, and in particular, the search for extraterrestrial intelligence. I've given this talk to some more general audiences of astrophysicists, most recently at McGill University for their Bell annual lecture. And it's got some background material. I think for a lot of people at PSI, you might find the background material things you already know. So we can speed through that, but ask me questions as we go. We don't need to wait to the end. What the talk is about is fundamentally about the Fermi paradox. I'll speak in some details to what the Fermi paradox is and how it came to be. That's Enrico Fermi, Nobel laureate, a nuclear physicist, Manhattan Project scientist, who dipped his toe in the water of the search for extraterrestrial intelligence a very long time ago, at the beginning of the 1960s. And his question, which I'll review, is so powerful that it's become known as the Fermi paradox. So, well, the second thing I want to talk about is something called the Drake equation, and that gentleman is Frank Drake. Frank Drake, who unfortunately just passed away last year, was a radio astronomer, mid-20th century radio astronomer who did many things, including running Arecibo for a very long time. Did just tremendous research, but many of you may know something called the Drake equation, which is a very simple probabilistic estimator, an algorithm to estimate the number of extant civilizations. And Drake coined this equation about the time in 1961 that he launched the first serious project to look for radio communications from extraterrestrials using greenback radio telescopes to look at 2 nearby stars. But the Drake equation is a very useful construct. And so I want to say a little bit about that. This is the Drake equation at the top. It's simply the multiplicative product of a whole bunch of factors that if you could estimate them all, they would spit out the number of civilizations with which communications might be possible. And so you need to know a number of different things. And I'm just going to try your patience in case you don't already know this. You need to know the rate of star formation. And if you then multiply that by the fraction of stars that have planets, and the number of planets that can potentially support life per star that has planets, and then you estimate the fraction of planets that actually develop life at some point, and the fraction of those planets that go on to develop civilizations once they have life. And finally, the fraction of civilizations that develop a technology that makes them detectable. Then you have a rate, and if you multiply that rate by a time scale, the characteristic length of time that civilization releases detectable signals into space, then you get a number. And that number is a global estimate of the number of civilizations we should be able to communicate with at a given time. That's called the Drake equation. Now, I'm going to pause on the Drake equation for a minute and talk about one of the important revolutions in the field of astrophysics and planetary science in the last few decades, and that has been, of course, the discovery of exoplanets that were not known in the 60s. They were speculated about, but at the time that Frank Drake was coining the Drake equation and going off and looking for extraterrestrials by radio techniques, there were no confirmed planets around other stars. That really, that discovery really only came in the mid-1990s. And the number of detections of extrasolar planets, of course, has exploded in the last 10 years, primarily because of space missions like Kepler that have really turned this from a game of a few tens of detections per year into thousands and thousands of detections. And there are different techniques. The transit technique that Kepler uses is the dominant technique of our time. It has its own selection effects. But there are other techniques like radio velocity, which is how this whole game got started. This micro lensing and astrometry and other techniques that you see there. But the important point is that we now know of many thousands of confirmed exoplanets. So
has that changed Drake's original estimate of how many civilizations might be out there?
well, I'm just going to talk about that. Thank you for asking. As a matter of fact, that's exactly where I'm going.
He told me to say that.
Thank you. Going back to the Drake equation, despite the fact that we now know that virtually every star has planets around it, that's of order unity. Maybe it's a half, but it's the first order. All the stars that we know of, at least in our galaxy, have planets orbiting. But so many of the other parameters are poorly determined. We do understand from astrophysics the average rate of star formation in the galaxy, which works out to be 3 to 10 new stars per terrestrial year. And as I said, the fraction of stars that have planets is now pretty well established to be of order unity. I put a half there just to be conservative. And with the kinds of facilities that are going to come online either soon, for example, 25 and 30 meter class telescopes later in this decade, or later in the form of future space observatories, we're going to get a good handle on the number of planets that can potentially support life per star. That's going to come within the lifetimes of researchers in the field now, not even very far off, maybe by the 40s. And we're going to get a good handle on the fraction of planets that can actually develop life. This is primarily through study of atmospheres of these planets around other stars. But despite the fact that we've got the rate of star formation down and the fraction of stars that have planets, we presently have such a poor handle on all the other factors in the Drake equation to answer your question. The estimates are all over the map still. In fact, estimates of the number of civilizations we should be able to communicate range from pessimists who'll say maybe of order 1 up to 10 to the 16th. So you can get any answer you want.
I'm surprised they don't have many that are much less than.
There probably are. Maybe I should stand corrected.
Yeah.
Right. There are pessimists. And, this is it. Right.
Yeah.
And the answer is 0.
By definition, The answer must be one
No, that's
or
fine.
more.
No,
No,
It's-
you're the one we don't count.
Oh, we.
See, it's the one number we can communicate with.
Oh, okay.
Right.
Well,
So-
some communicators ourselves.
Well, we don't do
So,
that very well.
so no, these estimates are all over the map. Now, what Fermi said, and this is just as true today in 2023 as it was in 1960, when Fermi came up with this, was he said, so if the number can be so high, Frank Drake, at a lunchroom conversation, where the hell are they?
Yeah, exactly.
Where are they? Why don't we see evidence of them? You know, I mean, I remember when I first read about this as a kid interested in astronomy. My first thought was, well, not necessarily, because Fermi's basic point was, why don't we just look out in the night sky and see evidence of them, maybe contrails from starships, or, you know, the galaxy would be rearranged by greater intelligences or something. I guess my first thought about it, wrong or right, but I remember my first thought was, do the ants in Manhattan know they're in an intelligent civilization super city, right? But nonetheless, what Fermi said at this little conference in the early 1960s that Frank Drake put on with Carl Sagan and a couple of other luminaries of the day still stands as a very important question. If the number can easily be high by our primitive estimates, where are they? Why don't we see any evidence by any means we can think of? And
They're all in
Yeah.
Roswell.
well, I was gonna say Star Trek answered that one. You can't contact civilization until they develop warp technology.
right. Right, it's sort of like, you know, the monolith in 2001, right? They buried it on the moon because they weren't interested in us until we could develop space travel and find a model.
Yeah.
So it turns out this has been a cottage industry. There are literally hundreds of papers that have been published responding to the question of the Fermi paradox. And this little infographic that I found on the web tries to, you know, kind of do a reductionist view of the sort of 10 leading kinds of answers that people have provided in all these papers that are out there in the literature. And they kind of boil down to three things. Three popular responses. One, few intelligent civilizations ever arise. So one of the first terms in the equation is really low, and that drives the whole thing down to a no answer. But alternatively, it could be that they exist. Here's number two. But we don't see evidence of them because the fraction who communicate is small. Maybe we're the only ones who developed radio, or maybe the phase when you use radio is a very brief phase, and the ways that you communicate might be completely different. Or it might be that the lifetime of intelligent communicative civilizations is short. For example, the AI singularity happens, and you know, then the AI is not interested in communicating with extraterrestrials, and we're all gone.
Another one that I saw that I don't think was up there is that gamma ray bursters completely sterilize vast radiuses around them. And civilizations don't have time to propagate very far out through the galaxy before they get sterilized by a gamma ray.
That might be, but this talk is actually going to provide a counter to that. Okay, so let's go there. Now, I want to talk about one more revolution in the field of planetary science in the time of my career. If you go back to the beginning of space age, when we mostly just had ground-based astronomy, and very smart people who were in the field looked out across the solar system with the high technology telescopes of their day. They looked at the terrestrial planets, and they looked at the giant planets and their satellites, and everywhere they looked, they didn't find any oceans. And they concluded, we now know incorrectly, that the Earth is a weirdo. It's the only planet with an ocean in our solar system. These oceans are very rare. That's a confirmation bias in a way, because we've since learned through spacecraft techniques that there are interior water ocean worlds whose oceans can't be seen on their surface, but they're just as real as the oceans that lie on Earth's surface. And the very first detection that was really significant came from the Galileo mission, which is the first orbiter mission to Jupiter. And that's Marky Kittleson, who was leading the magnetometer team. And that magnetometer team found the signatures in close flybys of the Galilean moon Europa. The magnetic signature of a currents flowing, induced currents from some sort of an ionic liquid like a salty ocean. Later, other lines of evidence came along, and I guess this is the most obvious one, which is Enceladus, where we actually see a subsurface ocean bending into space. In these images from Cassini, made in the early 2000s, actually, you can see multiple geysers going tens and even 100 kilometers into space, all erupting from the South Polar region simultaneously. And this was a huge shift in our thinking, because Europa had raised the question, but Enceladus, once we had two, it really changed the way that we thought about things. And as a result of this, Cassini got very interested after making these high phase angle measurements that show you directly in imaging that there are all these plumes. Then they established that the plumes are water and with some very interesting minor constituents in the water. And Cassini actually retargeted some of the flybys in the late 2000s to fly through the plumes at successively lower altitude to get better and better measurements with the ion and neutral mass spectrometers of material in the plumes. So sampling things that had come from that ocean and had been flew up to altitudes that Cassini could fly through. And at one point, Cassini made a flyby, I believe, as low as 25 kilometers off the deck of Enceladus. And
Alan, in the previous slide, your two previous slides now. So is that some kind of artificial thing floating into a plume?
oh,
This,
Yeah, I mean, it seems relevant to your talk here.
thank you.
it's a man of war.
This is definitive evidence that despite COVID, Mark is perfectly sharp. But we've now got a whole set of different kinds of evidence of these water ocean worlds. I call them WOWs, water ocean worlds, across the solar system. We see water plumes, and not just at Enceladus. There's also evidence at Europa, for example. There are geomorphological and geocompositional data on the surfaces of icy satellites across the solar system that indicate at least circumstantial evidence for other ocean worlds. There are magnetic signatures like the type that we discovered at Europa, and gravimetric signatures that also indicate that we've got water layers, liquid water layers beneath the surface all the way out to Pluto, which we could talk about, but I don't want to be giving a Pluto talk today. So,
But what were the contaminants in the water?
I'm going to get to that too. You apparently have a list of questions perfectly aligned with my slide. Thank you.
So Earth is still special because we have a surface of.
Yeah, in fact, one way to think about it is that the mid-20th century view, that if you look across the solar system and you don't see oceans, the Earth is the weirdo, was partially right. The Earth is the weirdo. In our solar system, it's the only one that wears its oceans on the outside, right? But they were wrong. There were no other oceans. Now.
Right.
And of course, I actually wrote a paper on this a long time ago in 2003. When the sun goes red giant, the temperatures out in the Kuiper belt for the dwarf planets will be approximately the temperature of Miami Beach today. And all those water ice crusts will become liquid for 100 million years. And people have done a good bit of work in the years since then and actually modeled what those atmospheres will look like. And that's a whole separate talk. So I'm not going to go there for very long. But what we now have is what I call a quasi-ubiquitous paradigm, that ocean worlds are common, but that they're typically interior water ocean worlds.
But they could be only common in our solar system.
Could be, but the physics that produces these water oceans beneath the surface is pretty simple physics.
And so you think it could be
And so we know that water is common across the universe, even in high
Sure.
redshift galaxies.
Sure.
We see that gas in the interstellar medium of galaxies across, we see ice grains also in clouds across our galaxy and other galaxies. I don't think it's much of a stretch to say that water is common in other solar systems.
Right, agreeable.
And if that's the case, then where you have cooler conditions, where you have water ice crusts, as you go down in depth, and the overburden pressure increases, so the temperature also goes up, then you can get to a point where you get to the liquid transition pretty commonly between tens and hundreds of kilometers down. And this is just very simple physics that it's almost unavoidable.
Sure. And so I guess my question then boils down to, in the exoplanets that we've seen, do we have any way of guessing how many of those types of oceans might exist in those planetary systems?
No doubt somebody knows how to guess that. But as you probably know, the detection techniques for extrasolar planets favor much larger planets, either in the transit or in the radial velocity, the two dominant techniques. And so we don't detect the things that are the size of Europa, except extremely rarely by some fluke. Later, with better technologies, we'll be able to see these kinds of worlds, and then we'll be able to study them too.
Sure.
Right now, we're mostly detecting super Earths and hot Jupiters and very different kinds of worlds than you expect to have in the water ice ocean. But I don't think it's much of a stretch to expect that there are lots of interior water ocean worlds around other stars.
Sure, I would guess.
I don't think- I would take that bet.
There is evidence.
I would take that as a scientist.
Now, so all of the icy, underwater ocean. You're wrong. Subsurface oceans, there we go. All the
Interior
subsurface-
water ocean.
Yeah, okay, interior water.
Yes.
Okay, all of those have so far been around other planets, so they've been satellites. I don't think we were able, has there been a detection of satellite around any of the planets we've?
Oh, there are satellites that have been found in other solar systems.
Okay,
But we don't have compositional information about
Right.
this.
would we, is there any reason that you couldn't have or a primary planet that has an interior ocean? I can't think of any
No,
reason.
of course,
Okay.
yeah.
Depends how
And in
far.
fact, it would just depend on the mechanism. You know, Triton is a good example for me at least, right? We know Triton is captured. It used to be an independent planet in the heliocentric orbit. Had it suffered a different set of perturbations, it might well have been sent into the middle or inner solar system. And it would have had oceans during the period that it was orbiting at these former climates. So it's perfectly possible. So I've made the point that there's been a revolution in detecting extrasolar planets, that we now know they're ubiquitous, and that water ocean worlds are common, but they're mostly, at least in our solar system, of this secondary type where the oceans are on the outside but the interior. But what this has done, and this is where my interest came in scientifically, is it's completely upended the old idea of habitable zones. Used to be that all this talk in the 90s and 2000s about the Goldilocks, you had to have just the right conditions, a little closer to the sun than 1 AU, and it wasn't going to work around a G star because you get a Venus, and a little further out and you get a Mars. And you had to be very precisely tuned for any given star in astrocentric distance.
Actually, Bill Hartman mentioned that.
But
Maybe
that's out the
and
window.
don't forget that the satellites are out for the
And-
planets, yeah.
And we now know that because we know there are water ocean worlds orbiting giant planets at distances way beyond it, so-called habitable zone, that this is really an old school concept. It doesn't really apply. If there are fishies in the ocean of Europa at 5 AU, or Enceladus at 9 or 10 AU, or Pluto for that matter at 30, 40 AU, depending on where its orbit is, they don't care how far they are from their star, because the conditions that create the liquid water, the temperature and pressure conditions, are independent of where their host world is orbiting. So, just to summarize before I go to the main part of the talk, 3 types of water ocean worlds that are now discussed in the literature. The first are worlds like the Earth, external water ocean worlds, we call them IWOWs, interior water ocean worlds, or type 2, IWOWs for interior water ocean world. And third, there has been modeling and speculation that some giant planets have high pressure interior oceans of water,
Oh, really?
particularly Uranus and Neptune. I put TBC there to be confirmed because we don't have a closed case from observational information. Maybe the Uranus orbiter will do that. Or maybe some fancy ground-based technique in the microwave, for example, will do that. But we don't have anything more than papers in the literature with a little bit of modeling to suggest this might be possible. Now, let's talk a little bit about what the astrobiologists say are the conditions for the requirements of life. We're working our way through the Drake equation. And we now know that stars form frequently and that planets form frequently around stars. What do we need to have life? Astrobiologists, probably myopically, because there are probably ways that we haven't thought of to have life, but from our own experience, there are just 4 conditions that are commonly thought of that we need. We need liquid water. Well, we know there are lots of worlds with the liquid water now. Sources of energy to make the chemistry go. Biogenic elements that you can build biology from, particularly carbon, hydrogen, oxygen, nitrogen, sulfur,
Why were they put in
and
that order
phosphorus.
for that?
Hmm?
Why were they put in that order?
Oh, you can pronounce it.
Yeah.
Oh.
It's not order.
I don't need a physicist, I would just put it in.
It's not a condensation sequence, and it's not their abundance, solar abundance or anything else.
I was looking for hidden meanings.
Somebody just made an acronym.
Okay.
And you need a stable environment, and that's very important. You were asking this question about the gamma rays. The gamma ray bursts can sterilize things for a very large distance away from them. There are lots of lethal astrophysical conditions, supernovae, for that matter, novae and supernovae. You can have stellar flares. You can have all kinds of bad situations that create unstable environments for biology.
Yeah, I like the gamma reverser idea because if there was a bunch of spaceships throughout their region, they'd all be zapped.
They'd be zapped too.
So the germ, so to speak, wouldn't get to the next civilization.
So I'm going to get back to exactly that in just a few slides. But first, I want to talk about these 4 conditions. And so let's talk about what we found in our solar system in the plumes of Enceladus. By flying the Cassini ion neutral mass spectrometer and this Cassini dust chemistry instrument through those plumes, we find mass spectra like these that show all kinds of interesting signatures here. For one thing, notice all the sodium. This is salt water. Secondly, though, we're finding not just the sodium, but we've also found organic species that have significant molecular weights, hundreds of daltons, and concentrations on the level of from parts per million up to several percent. Macromolecules with aliphatic and aromatic constituents, functional groups, and different kinds of water solubility, depending upon which plumes and which measurements have been made. We found both types. This is getting really interesting. Not just salt water, but loaded with complex organics. And to top it all off, there's evidence from the Cassini mission that there may be hydrothermal vents in Enceladus's ocean. You know, the hydrothermal vents were a huge revolution in terrestrial ocean biology when they were found. They basically are places where there are energy sources to drive biology that were completely unexpected by the oceanographers and the biologists when they were discovered in the 1970s with these remotely operated deep sea vehicles. And around these vents, in many locations, whole colonies of plant life and even animal life, very large worms, for example, were discovered with their chemistry and the way they make a living, if you will, driven by the energy from these hydrothermal systems. So when Cassini started to turn up evidence that Enceladus may well have hydrothermal vent systems, it got a lot of people's attention. And the first thing they discovered was excess molecular hydrogen in the ion neutral mass spectrometer plume data. It's hard to explain the H2 except for vents, but they also found 2 other lines of evidence. They detected nanometer-sized silica particles whose composition and size indicate hydrothermal reactions at greater than 90 centigrade. That are the kind that we find in terrestrial hydrothermal systems. And in 2017, evidence that the energy budget that's available at Enceladus to do this is more than 10 gigawatts of heat spread around the oceans of Enceladus to drive these kind of systems. So there are a whole network of lines of evidence of the possibility of hydrothermal vents that really start to suggest that not just the composition is right, but they're the energetics to drive biology down in those systems. And so if we take the scorecard for what the astrobiologists would say we need for life as we know it to plausibly be able to evolve, we can check all the boxes. In places like Enceladus, you have liquid water, biogenic elements, salts, heavy organics, a suitably stable environment, and evidence for energy sources. And that's a nice quote from Cable's 2021 paper reviewing all this. This is now established fact. So here's the thing, and here's where the original part of what I'm happy to tell you begins. And it's this. And it really comes off the question you were asking about these threats, like the gamma ray bursts. If you live on a world like the Earth, where the ocean is on the outside, on the skin of the planet, you're subject to many, many constraints as to whether you can have a stable environment.
But you have an atmosphere.
You have to have an atmosphere. You have to be the right distance from your star. You have to have some shielding against ultraviolet light. You have to have a magnetic field to screen out the charged particles and cosmic rays that are damaging to biology. In fact, for worlds like the Earth, where the ocean's on the outside, there are many kinds of threats that don't apply in these interior water ocean worlds. They don't care about astrocentric distance. They don't care if their planet or host satellite is in an eccentric orbit. They don't care if the obliquity is varying all over the place, because where that ocean is, it doesn't know about any of that. It's not coupled to it. You don't need tidal locking, or you don't need non-tidal locking. It just doesn't care.
But you're confined to the ocean.
That's right. So there's no equivalent of going up onto land.
Right.
But still, you don't even care if you're in a multiple star system. You don't even care if your star is a red giant. You don't care if there's supernovae and gamma ray bursts going on, because you're protected by this roof
Right.
of rock and ice that's kilometers thick, that's
Right, but
insulated.
but that's the thing then. How would they communicate?
We're gonna get to that. This is a talk about the Fermi paradox.
abstract, but
You see where I'm
yeah,
going?
we'll get to that, but I do have a question about, shoot, I lost it. Just continue on, I'll think of it later.
Okay, please do. Yeah, I do that all the time. So,
And I can tell you, the worse is gonna work.
so going back to the Drake equation, for the fourth time now, if you look at the terms that are in amber in this slide, the discovery of common interior water ocean worlds gives us pretty good hope that several of these terms that we can't pin down yet, the number of planets that can potentially support life per star, the fraction of planets that may actually develop life at some point, and maybe even the fraction that become intelligent life and civilizations is plausibly a lot higher than pessimists would suggest.
If you look, being pessimistic, it seems to me that one of these interior water worlds, even if life developed there, it would be really hard for intelligent civilization to develop that could break through to the other
That's
worlds.
exactly where this talk is going. So now let's go back to the Fermi paradox, because exactly this is the logical conclusion. You've already reached it, right? So think about this. If there are, that this is a huge leap. So let me separate what we know, which is we have the conditions appropriate in water ocean worlds in our solar system for life to potentially develop. We don't have evidence of actual biology yet, much less advanced life forms, much less intelligence and civilizations. But what the heck? This is planetary science. So just suspend the fact that we don't have that evidence yet, if life and actually intelligent life might exist in these kinds of worlds, then the thing is that same shell, that same insulating layer that protects them of ice and rock overhead cuts them off from communication. If they're, even if they're doing radio and TV, it never leaks out.
But on the other hand, if they're, you would think if they're not intelligent, I mean, you know. We never thought at the beginning that we're gonna go on the moon because there is no air there, and you know, and then we get the technology to get spacesuits and rockets to go there.
Sure, the point I simply want to make is that if intelligent life develops in some of these worlds that are probably very common across the universe in very large astronomical numbers, that they are this very same thing that makes it a conducive environment for life and stable conditions, simultaneously cuts them off from most forms of electromagnetic communication.
And there certainly wouldn't be like accidental, like, you know, we've been.
It's like, we've been using radio for 70 years, 80
Oh,
years.
yeah.
right?
They're not purposeful.
That's
It just
so-
wouldn't purpose,
We
it would have to
wouldn't
be
know.
purposeful.
But then the question is still, Earth is still special, but how special is it?
Well, so let me just get further and further on this limb before I solve myself off.
I'm already in my
I've only
mind,
got like 4 more slides, guys.
well, I'm already in my mind started developing a spaceship work on that.
Okay, so the thing is, if you were an intelligent whale or worm or whatever kind of being in one of these worlds, you might not know there's a sky in the universe. Now, you might be inquisitive and say, what's happening in the roof? And they might develop a technology to tunnel
There
up.
was a big quartz lens that developed. And they could see through it.
I think the important thing is what you're getting at is all of these civilizations are cricket.
They're what?
Cricket
Crickets.
from Hitchhiker's Guide to the Galaxy.
Oh,
They were a civilization very much like Earth, orbiting a star in a giant molecular cloud. They'd never seen another star.
And they didn't know.
And a spaceship crashes on their planet. And they go out and see all the stars out there and conclude they need to go.
Okay, I got it.
And that's,
So this is an analogy.
it's
So
a cosmology question.
As I
What their
said here-
cosmology is.
would such civilizations even develop astronomy and learn that there's a sky above their world? Seems less likely than for those of us in these dangerous surface ocean planets. And even if they did figure out that there's a universe up above somehow, they might be very naturally biased to think that only other civilizations like themselves in these conducive environments, just like they
Certainly,
they might think no one else is communicating.
Right,
Right,
right.
because they're all like us, they're in these insulating oceans, right? So that obviates many of the rationales for SETI. Because
Right,
it sort of
that's
makes
right.
it,
But then,
it's
so you can't,
unintuitive,
you're right, so you can't communicate, but then, I mean, it's there, you know,
but it,
explore, they're gonna
one more thing. The other thing is, they're also biased against space exploration, space travel, for a lot of reasons. First,
makes you think we're not.
well, we are, but they're more so. And here's why. First, it's not clear that intelligent species living in these interior water ocean worlds would know of the external environment. If they do, it's unclear that they would explore, much less inhabit, this lethal environment up on the surface, right?
And it's gonna,
But they're more technically challenged. We have a hard time with space flight, and we don't have to bring oodles of water with us, right? If you're an intelligent whale or worm and you have to bring all that water, then the rocketry is a lot harder.
I would say you don't have to worry about
solar
solar
base
base.
at that point.
So first off, everywhere in the solar system other than Earth is a colossal hellhole that we don't want to go to. It's an incredibly inhospitable environment. in the
Except maybe
center.
these oceans.
Well, except these oceans, yeah. But so if they are technically capable of reaching the surface, and they would have to be a technological civilization to do so.
But
They,
just the
they
rocket
would
equation,
probably-
it's harder if you have to bring all that water.
Why would they
you're
have-
on a much smaller world. In almost every case that we've had,
Geez,
the G's are way lower and there's no atmosphere.
that's a really good point.
So getting off the surface with a bunch of water is a lot easier. We're close. If the Earth were, what is it, like maybe 20% more massive there would be no way to get into space using chemical rockets.
Yeah,
Yeah.
this is a really good point, Walter. I'm glad you brought it up because I had not thought about this aspect of it. It's really good.
Yeah, so I think they could, if they could get to the surface.
It's true.
they could-
So I'm gonna conclude here.
Well,
If you don't mind, I'm just gonna,
Yeah,
that was the last, then we can just have open conversation, right? So perhaps it's the purpose of the talk is to have you think about something fun. It's a little bit different. So perhaps the answer to Fermi's question, where are they, is simply they're at home in their type 2 water ocean bubbles, where they can neither communicate or easily develop space travel. They're everywhere, but they don't communicate.
I
and they
think you
don't visit.
underestimate intelligence.
How do I estimate intelligence?
You underestimate
Oh.
intelligence.
Maybe, yeah, I'm,
And so I
But
perfectly
again,
happy to
but
think they can figure out a way to get to Earth.
But where are they?
Well, I didn't say they could have done it by now. Maybe it takes more than 4 billion years.
So I think actually there's part of what you said earlier. And going with what we know about planets. There's a very good chance that worlds with a long baseline, many billions of years, because that's what we have concluded based on our experience it takes to develop complex organisms and all of that. Planets like Earth may be much rarer, almost certainly are much rarer than these.
Yeah.
So these civilizations, when they appear, are much more likely to appear around small stars, because so many of the stars in the galaxy are small, and they don't care about tidal locking, but tidal locking will sterilize away surfaces.
oh,
So they'll come up, they'll go, they actually, unlike us, will look at every spherical icy body as a potential colony. We can just go there. We burrow down, we just burrow up, we'll make a colony there. Look at there are hundreds of places we could go, thousands in our own solar system. We might never even need to leave. And we don't care what the star does. It's going to live for 3 trillion years once they figure out stellar lifespans. Yeah. Why do we need to travel? But if they were to travel, they would go to other places like that, or they would assume that rocky bodies are sterilized. So they wouldn't even think to communicate or look at us.
And again, how
We
would,
would be kind of parallel play.
right, so how would the question is though, let's say that they burrow up and they look for others to burrow out, how do they communicate with each other? Not with radio or not with.
Oh, well, they might, but they're not
feeding it
sending
out.
up beams to
And
other
they're not
stars.
looking for
They
it.
might, but unlike us, as soon as we develop space travel, we start thinking in terms of Star Trek. Because there's only one habitable world here for us. But that could be around other stars. So now we think about going there. But if you evolved, let's say, an intelligent civilization evolves on 7.
or
Europa, but it comes out and starts looking around the solar system and it goes, wow, there's hundreds of these things. We're just gonna hang out here.
so it's a lot easier for them because they don't have to do interstellar travel.
That's right. They don't have to think about the interstellar option. They can this for
Couple of
2 trillion years without ever leaving.
Got a couple of points I'd like to interject here. One is that remember in our own history, we looked at other planets in the solar system, which included, the moons around Jupiter and all that. And early on, we're assuming that intelligent life was everywhere, that these were worlds where there was life on them. That was just assumed. And but I would argue against, or I don't want to say argue against, I say there's some perhaps challenges for having sub-ocean civilizations. And that is that evolution seems to be driven by challenges, by stressors and environmental stressors. And so the question is that when you're on the surface of an object like Earth, you've got wide temperature variations. You have all kinds of climatic type stuff. There's a lot of environmental stressors that you might not find in an ocean world. And so maybe you can get life there that would be simple life, but you can never get enough evolution going on to result in a civilization. And my own view is that, I think Earth, that it's quite possible, given the chaos of the early solar system, that yeah, we had life forming in these icy worlds like Ceres type objects, and that one of them came along and crashed on the Earth and contaminated it, and hence here we are. But I think the environmental stressor issue for civilization is something that might limit civilizations to Earth-like objects in the Goldilocks zone.
Well,
That'd be a different answer to Fermi's paradox, but another valid.
I'm going to push back on that, environmental stressors. This is the point that I was thinking about earlier, is that we are acutely aware of all of the troubles we have here on the surface. And we say, oh, well, if you go to a subsurface ocean, you don't have those problems. Well, true. Do we know all the problems that would entail having a civilization in the ocean? No, or at least I don't. I haven't thought about it. And I'm thinking that perhaps we're biased in saying it's easier to survive in a subsurface ocean than on the surface. It may be true, but we certainly are biased.
No question.
Well,
Yeah,
and
that's-
it is possible to develop complex life in an ocean.
We know that.
Functionally, if you live in an ocean, air is every bit as real a barrier as the roof of Europa. You go down on the surface, you're dead. And yet, an astonishing variety of complex organisms, including things like octopi that are really very smart.
But it's still interacting with the surface of the planet, though. There's a lot of ocean stuff that's driven by interaction with.
I think Walt's point is that here we have an example of an ocean
Yeah.
where you don't have the environmental stressors Mark was talking about that we do on the surface. And yet you can get very complex life and maybe even some smart life.
Yeah, and evolution is not just driven by stressors. Sometimes it's also, a raw cosmic rays changes something.
Yeah, it's
you know,
Well, that's what happens on
slower.
the surface.
It's much slower.
So,
That's true.
No, but you have radioactivity from the rocks at the base of the ocean.
Yeah.
There might be other ways to
Yeah,
get the
that's-
same result.
so the one thing that I would say from the Earth's experience that actually would track with this is for the first 2 billion years or so of our biosphere, it was an environment that was probably very similar to what you would see inside these oceans, because life was all archaea, all chemical based metabolisms, and most of it probably concentrated deep in the oceans near these hydrothermal vents,
And a pretty poisonous atmosphere.
Yeah.
and a pretty poisonous atmosphere above for them. But for whatever reason, and I guess the current theory is the nickel famine, there was a change in the ocean characteristics that gave other organisms lead, and now archaea are basically gone. I mean, they still exist in a lot of environments, but the biosphere is dominated by photosynthetic driven organisms. And that part may be a problem. If these worlds stay in a very stable environment for archaea, we don't see any evidence that archaea evolved into multicellular organisms at any point. And maybe they don't.
No, but we do see evidence of these hydrothermal vent columns.
We do, but that's presumably post the.
Somehow we get from A to B, we get from archaea to
Well, that was through,
those kind of colonies.
that was probably through cyanobacteria,
Yeah, I don't know that, no.
but we don't have the answer yet. But it's just, that's more of a gate than I think just the changes in evolution would drive. But maybe these worlds would go through the same, right? Because in the Earth's case, the Earth's core cools a little bit. And now nickel is staying at the core, it's not getting pushed into the oceans, concentrations drop by orders of magnitude, and methagenesis doesn't work anymore. And now you have to change the metabolism, and that's a stressor that drives evolution.
But something like, I mean, not exactly that, but we don't know if something like, similar couldn't happen in the subsurface ocean world.
Yeah.
I mean, stuff is, you say stable, but stable doesn't mean unchanging.
I mean, using the Earth again as an example, could, the complex Earth life arose because of the great oxidation event. And where bacteria started generating oxygen, accumulated in the atmosphere, but also was increasing in the shallow oceans of the time. And so I'm wondering if this could happen in a purely contained, ocean environment, or to what extent having that atmospheric release and accumulation was important to then the subsequent development of multicellular life on Earth.
But wouldn't the ocean also, the subsurface ocean does not interact with the crust? Just much slower, stuff happening to the crust from
So I don't
outside?
think, I would say, I'd be contrarian and say that till we can explore the oceans of Enceladus and Europa, I don't think our imaginations are good enough. Right? The same way that before we sent spacecraft like Voyager into the outer solar system, the common view of all the icy satellites was they were just dead, boring ice balls. And we had no idea of the complexity and diversity of expressions of nature that are out there. It was just thought it'd be cold and everything.
Boring.
Yeah.
Why are those shells stable? Why don't they, through earthquakes and meteorite impacts, fall down and there's no interior ocean?
We had a confirmation bias about it. There were really strong clues, like that there was intense tidal heating in the Jupiter system, and that would
But
probably.
hindsight's.
We started with this history. We started with
But we do see the crust is rearranged from breaking the regions. There is interaction between the subsurface ocean surface.
Right. The fact though is, regardless of what's going on at the top, in the low pressure environment near this, whatever the ambient surface temperature is, it's just the perfect gas equation, right? It's just as you go down and the pressure increases because the overburden increases, the temperature will go up, and you will reach a place where the water ice becomes liquid water if the layer is thick enough.
So you think that here's the crust, here's an intermediate ice layer, that really helps stabilize the rocky crust.
Well, it's the water ocean that's in between the rocky crust.
Oh, the ocean.
ice that we're talking about.
So let me get this straight. Here's a rocky crust. What comes next?
Well, in these worlds, it's an
rocky
icy crust.
The rocky crust, yeah.
It's an icy crust, right?
Well, it's not rock.
No, like Enceladus, Europa, Titan, Pluto, Triton, going down the list of all these water.
I think
ocean-
I think
water
the-
H2O ice crust.
I think the entire Colorado office has its hand up.
Oh. Say something.
Yeah, unmute.
Yeah, I just had a thought about an earlier point about how evolution might be slower in Enceladus because there aren't environmental stressors and stuff like that. But then also there wouldn't be any mass extinction events like meteorites or huge solar flares that would slow down evolution even further. So then considering the fact that when Enceladus was created, I guess, in the first place, it would have had a lot more time to evolve to a much more intelligent state than maybe we are in.
Exactly right. Yeah,
You can view that both ways.
I know, because you could say that, thank goodness that we had a KT event so that the mammals could rise. So I mean, Walt's right as usual.
Mass extinctions are bad things.
Depends.
Yeah,
But
it's-
what it does is it forces a reset.
Yeah.
So it takes evolution in a random direction.
Well, again, intelligence isn't driven by evolution.
No,
It's not like evolution doesn't prefer intelligence. At least I don't think there's any evidence for that.
I would say
Obviously not.
Yeah.
right? I mean, the evidence is that we have, what, 1 billion different species that have inhabited the earth over time. And we have arguably a handful that are intelligent in some respect. You know, I'm counting the whales, the octopuses, right? Right? Or maybe if you want to call what your dog cat has some form of intelligence, that too, but it's a tiny fraction of all these trials of evolution.
Yeah.
And once a certain level of intelligence rises, then it takes over and directs its evolution.
Yeah,
Really?
perhaps.
Yeah, I guess where would we draw the line in that direct equation for what counts as intelligence? I mean, that's why there's a separate communication.
Well, it's intelligent enough to
Because it would be
communicate. with
Really
another
interesting if like cat, dog level intelligence was
Yeah.
on another planet, that would be fascinating.
Of course, but for
As
the
opposed to
purpose of the Drake
planets.
equation, the intelligence has to
Yeah.
be an intelligence that can create a way of communicating over interstellar distance.
Yes.
Right, hard to imagine cats and dogs.
Yeah,
However,
So then we're not intelligent, but because we do interstellar distances.
We do,
Do
right, right, whether we want to or not.
Yeah, well, it's the
But-
question of what's the amplitude of the signal? No, could take the nearest star, could a civilization, if we took our instruments to the nearest star, could we detect the radio waves we're sending out, or would the amplitude be too small?
Actually, so that was the kind of thing that people like Carl Sagan were calculating in the 1970s. And I think even in the 1970s, it was clear that we could detect an equivalent Earth
Oh, we could.
from something like 100 parsecs. With today's
Okay.
technology, probably further. So,
Okay,
so the answer is yes.
yes, yeah.
We would,
how many
if,
stars are within 100 parsecs?
well, a lot, it's roughly 100 cubed. Something like that, so that's a million.
so, but, you know, one thing to keep in mind when you talk about intelligence and you say, okay, what cat and dog intelligence was there? What you're really talking about is technological intelligence, because if we accept the findings from last week of the earlier hominid species, there have been intelligent hominids smart enough to draw symbols and bury their dead on this planet for 500,000 years. And there has been a radio communicating civilization on this planet for less than a century. Well, I mean, capable of sending it anything out into space that would be received by anybody else.
Yeah.
So we've only just become a technological.
And this was a point that Sagan made many times. And so if that L, the lifetime is short, in his view, that's because we annihilate nuclear holocaust. But for any reason, whether it's an external threat or something this civilization or the environment does to itself, if L is short, that can answer the Drake equation.
Right.
Because intelligences are coming into being
And we-
all over the place, but they're
Destroy
stuffed out very quickly before they can communicate with one another.
On the other hand, you could have an intelligent civilization that comes to Earth 200,000 years ago and could find someone to talk to.
Mhm.
I mean,
But would-
they were not, modern humans are maybe 100,000 years. So 100,000 years ago, they could have come up on these nomadic hunter-gatherer civilizations and actually eventually had a conversation with them. It would have taken time to explain it, but they are us, so they could have come.
So I know we're at the end of the hour. I hope that I opened your eyes a little bit
Yeah,
to
no,
just think about a different way to think about the Fermi paradox, that it's not about necessarily civilizations on the skin of planets in these shooting galleries where astrophysical hazards and impact hazards and other things make it hard to imagine civilizations like ours are common. It might be that they're ubiquitous in these water ocean worlds, the interiors, but they just don't communicate because they're insulated. from
And then,
communication.
of course, we really only looked at biological life as we know it, and not some, esoteric stuff, like. Which a lot of science sections do.
So Alan, I guess I'll say thank you very much. It's top the hour. Thank you very much for your talk. My final word is, in space, no one can hear you bark.
Thank
So,
you.
yeah, thanks. Thank you. We can stop the recording.